So you rewrote a performance-critical part of your application in Rust because you heard it's blazingly fast. But unfortunately, the old version is still faster. Luckily, a senior Rust developer notices the problem right away. Calling the collect method here is not needed. It creates a vector we never use. We only need to square the values and sum them. Once we delete that collect, the function becomes 3 times faster. And that's the key to writing blazingly fast Rust. Knowing exactly when and where performance can be achieved through small tweaks to give you the lightning fast performance you were promised. In this video, I'll show you 4 optimizations you can apply to almost any Rust codebase right now. And the last one is something 99.9% of developers never even think about. Yet it delivers one of the biggest performance gains you'll ever see. Let's dive right in. The previous example was just a warm-up. The actual example we're going to focus on is the top users function. It reads a 20 million line log file and returns the 10 most active users. This is a very common pattern in production code. It walks the log one line at a time. Each line is split on commas, and the second field, index 1, is the user ID. Each ID increments its own counter in a hash map. And at the end, we sort the counters and return the top 10 users. Run this on 20 million lines and it takes about 1.5 seconds. That's our baseline. Every optimization from here will be measured against it. Optimization 1. Stop allocating memory you do not need. This one applies to almost any hot loop in Rust that touches strings or own data. This toString copies every user ID onto the heap. 20 million lines means 20 million allocations. And this clone copies the same ID a second time, so it can be stored in the map as a key. Both copies exist for one reason. If we look at our hash map definition, its keys are owned strings, so every key creates a heap allocation. So let's change that one type. Instead of creating a new string, the key becomes a string slice, which is a view into the existing log string already in memory. Now watch what happens to the loop. On line 4, the toString is gone. User is now a string slice itself. The clone gets dropped as well. And because the key is already a reference, the ampersands in front of contains key and getMute are no longer needed either. Nothing in this loop allocates memory anymore. The ranked list uses those same string slices, so it becomes a vector of string slices too. Now one thing is left, and this is the part we have to be careful with. The function still promises to return owned strings, but ranked now holds string slices. So right at the very end, we convert only the 10 returned string slices into owned strings. That's 10 allocations instead of 20 million. That cuts the runtime from 1.5 seconds to just about 1 second. A 30% speedup just by removing unnecessary memory allocations. That's a great first optimization. Now optimization 2. Avoid repeating work. Hash maps are a perfect example because it's easy to accidentally perform the same lookup multiple times. A hash map does not store its keys in a list. It stores them in a hash table. Every time you ask the map for a key, it has to hash the key to find the right slot. So we can see that this line hashes the user ID to check whether the key exists. Then this line hashes the same ID again to insert it. And finally, this line hashes the same ID a third time to update it. This is essentially 3 lookups for every line in the log file, which is a lot of repeated work. Instead, we can use the entry method, which does all of that in one lookup. The entry method finds the slot, inserts a 0 if the slot is empty, and hands back a reference to increment. Another simple adjustment and another 12% shaved off the runtime. Optimization 3. Use every core you have. Right now, this whole function runs on a single thread, while the other 11 cores on this machine sit idle. This counting loop is the bottleneck. 20 million lines, processed one at a time, on one core. Each line only updates one user's counter, and the lines never depend on each other, so they could run on many cores at once. The catch is that a for loop is sequential by definition. It can only ever use one core. Let's make one small change before we introduce parallelism. We'll rewrite the loop as an iterator chain. Lines walks the log, and fold accumulates the results into a hash map. It's still the same single-threaded work, but now it's written in an iterator chain. Now we can bring in the popular Rayon library. Rayon is a library that makes it easy to parallelize work across all of your CPU cores. To use it, we simply replace lines with parlines, and Rayon automatically splits the log into chunks and distributes the chunks across CPU cores. Each core builds its own private hash map, so all 12 cores can count at the same time without waiting on each other. The final piece is reduce. which combines those per core maps into one by adding the counts for each user. And that drops us from 100 to 90 milliseconds. We went from 1.5 seconds down to under 0.2, more than 7 times faster. Now, for the next optimization, let's switch to a different example. Imagine our service keeps track of every live user session in a vector. Every few seconds, it sweeps that vector and drops the sessions that have gone idle. Here's an optimization that 99.9% of developers never even think about. By default, remove preserves the order of the vector. That means every element after the one you removed has to slide over by one position. For example, if you removed a session near the front of a vector with 1 million sessions, then the other 999,000 sessions all slide over by one position. That's an enormous amount of work just to preserve order. And for our use case, order does not matter, because we don't care what index a session is at in the vector if we're simply removing them. Because order doesn't matter, we can use swap remove instead. Rather than shifting every element over, swap remove takes the last element in the vector and swaps it into the position of the element being removed. One swap, and you're done. The only downside is the vector is no longer in its original order. Now this one change is going to give us a mind-blowing performance gain. But before I reveal the results, can you guess if it's 50% faster, 2 times faster, 100 times faster? It's over 7,000 times faster. That's right, I didn't misspeak. 7,000 times faster. Swap remove has been in the standard library since Rust 1.0. It was only one line away this whole time. Most developers just never knew it was there. Now try these Rust optimizations on your own codebase, and let me know in the comments which one had the biggest impact. And if you want to learn how to write and optimize production-grade Rust code, check out our Rust Lab Accelerator. It's our tailored mentorship program where we help developers go beyond YouTube videos, build production-grade Rust systems, and land their first Rust job. You can join the waitlist for our next cohort by heading over to letsgetrusty.com/join, or by clicking the link in the pinned comment below. When you join the waitlist, we'll also send you our Rust developer roadmap as a small gift. So tap the link, join the waitlist, and I'll talk to you very soon.